Let's do our first kinematics problem using the equations. Although it would be good practice to go back afterwards and solve the problem again using your graphical approach. Here's the problem. You're in your car at a red light, waiting to get on the highway. The light turns green, you accelerate at a constant rate of 5 meters per second squared for 6.6 seconds. At that time, you see a highway patrol car, notice you're going too fast, and slow down. It takes you 60 meters to reach your final speed, the speed limit, which is 25 meters per second. It's a good idea to pause the video, attempt the problem, and then go back and forth. If you need some hints, watch me set up the problem, stop the video again, attempt to finish it on your own, go back and forth until you've finished. The first step is to figure out what the problem is. Often, drawing a picture is the best way to help your mind figure out what's going on. In this case, we're starting from some location. I'm going to call that point A. And we know we're at v equals 0 at point A. At some later time, we're over here. And we're moving. And VB, we don't know. But we know it's over the speed limit. We've moved a certain distance, which again, we don't know. But we do know during this whole time period, we were speeding up with an acceleration of 5 meters per second squared, and it took 6.6 seconds. And at some later point, you're moving at the speed limit of 25 meters per second. This distance was 60 meters. And during this time, your car was slowing down. We do not know the acceleration. We do not know the time. Maybe that helps. Maybe you can attempt the problem now. We're going to use kinematics equations. And our kinematics equations are all based on the fact that the acceleration is constant. Can we go right from the beginning to the end using kinematics equations? No, because the acceleration is not constant over this entire time period. It's constant from A to B. We have constant acceleration. From B to C, we have constant acceleration. But it's not constant from A to C. It abruptly changes in the middle. So how are we going to solve this problem? We're going to split it into two problems. One going from A to B, where we have constant acceleration, and one going from B to C, where we know we have constant acceleration also. Remember, there are 5 parameters of interest. I like to make a little table every time I do a kinematics problem using equations. I make a little table with my 5 parameters of interest. Delta x, v initial, v final, acceleration, and time. I make a little table like this, and it helps me organize my thoughts, figure out what I know, and figure out what I don't know. But there's something we have to do before we can fill that table in. We have to define our origin and our positive direction. So I'm going to call this point right here x equals 0, and the right will be my positive direction. Now I can fill these numbers in. Otherwise, how would I know if my delta x was positive or negative? How would I know whether my velocity or my acceleration were positive or negative? I have to define my origin and my positive direction. While we're speeding up, we're going from A to B. I'm going to call delta x AB. My V initial, I'm going to call VA, because I have two problems here. I don't want to call this one V initial, and then over here, I'm also going to have a V initial. I'm going to get confused. So I want to indicate that they're different. I'm going to call this one VA, and I'll call the other one VB. You'll see when we get there in a second. My final velocity is V at location B. My acceleration, I'll call it AB. And my time, I'll call it TAB. Those are the 5 things I'm interested in. What do I know? I know I start from rest. I know I accelerate in what direction? The positive direction, 5 meters per second squared, so that's a positive 5. And I know the time is 6.6 seconds. With these equations, if you know any 3, you can solve for the other 2. That's typically true, unless you have a bunch of zeros. But in this case, it'll work. We can solve for the delta x, and we can solve for the final velocity, the velocity at point B. But let's figure out what we know and don't know going from B to C. This is our table. I'm calling our displacement delta x BC for this time interval. The initial velocity is just the velocity at point B. The final velocity is the velocity at point C. You get the idea. Let's fill in everything we know. Our displacement is positive 60. We end up 60 meters in the positive direction from where we started. Remember, this is not distance. This is displacement. It can be negative. Our initial velocity, we don't know. Our final velocity, we do know. It's 25 meters per second in the positive direction. We don't know acceleration. We don't know time. So we look at this and we say, wow, we're missing 3 items there. We can't solve for those with only 2 pieces of information. We need 3 things, and we can solve for the other 2. But what do you notice about this? Something that might help us solve the problem? The initial velocity, VB, for the slowing down portion, is the same as the final velocity, VB, for the speeding up portion. So we can solve for VB when it's speeding up, plug that in to our slowing down problem, and solve for the other unknowns. Okay, let's do our speeding up first. We can pick an equation that's missing delta x and solve for VB. So here's an equation that's missing delta x. We know that V final is what we're calling VB. V initial is VA, that's 0. Our acceleration we know is positive 5 meters per second squared, and our time is 6.6 seconds. And we get our final velocity, 33 meters per second. So now we can plug that in. This is now, we know, I'll write it in a different color. 33 meters per second. While we're at it, we can solve for delta x AB. I'm going to use this equation. V initial is VA is 0. I know my acceleration. I know my time. Don't forget to square it. And I get 109 meters. If you haven't done it yet, pause the video and finish the problem. We have 2 unknowns, acceleration and time. We want to pick an equation that's missing one of them so we can solve for the other one. If I want to solve for acceleration, I'm going to use an equation that's missing time because I don't know the time. Otherwise, I have to solve simultaneous equations. Why do things keep disappearing over here? I don't know. Okay, I think those equations are correct now. So I want to use this equation. My final velocity is vc, 25 meters per second. My initial velocity is vb, and I've got 2. My acceleration is what I'm solving for, and delta x is positive 60. And I get my acceleration is negative 3.87 meters per second squared. Now we know everything but time, so we can pick any equation with time in it. I'll pick equation 1 since that looks like the simplest one to use, and I'll solve for time. So the kinematics equations, it's fairly simple solving these problems if you're careful with your minus signs. Define your positive direction, keep track of what's negative, make sure you put the negative signs in there where appropriate, and you'll have no problem. So let's take a look at what we got. The distance in the first section, 109 meters. The distance in the second section, 60 meters, a total of 169 meters. We know our initial speed, our intermediate speed, our final speed. We know the accelerations. We know the time was 6.6 seconds while we were speeding up, 2.07 while we were slowing down. We could add them together to get the total time. So I think we've figured everything out for this problem.